So today's lecture is going to be very algebraic in nature because we're going to be going through things. Now, last day I introduced the concept of an inverse. Now, does an inverse always exist? No. So we're going to talk about when does an inverse of a matrix exist. So first of all, let's say that we have n by n matrix A. So first of all, it has to be square. If it's not square, there's no inverse, there's no discussion. Now, A inverse may exist, it may not exist. So definition, if A inverse exists, then we have a few different things going on. One is that A times A inverse equals A inverse times A equals the n by n identity matrix. Okay, that's the first and simple one. But it also means that if I have a system of equations written in this form, and we showed this last day how to do this, to write AX equals B. So I take my system of equations, I make A my coefficient matrix, X is the vector of unknowns, and then B the constants on the right-hand side. Then this will have the solution X equals A inverse times B, which is beautiful. Now, it isn't always efficient to use an inverse to solve a system of equations. Inverses are used for many things. This is just one of the possibilities. So if the inverse exists, all these things can happen. If the inverse does not exist, that means I cannot do this. It means there's not a unique solution. So one of two things. If A inverse doesn't exist and I have a system of equations, then either that system is inconsistent or that system is dependent, but I do not get a unique solution. Now, if A inverse exists, we say that A is non-singular. Now, that's kind of a strange word. The inverse existing we think of as a good thing. And saying it's non-singular almost sounds like a bad thing. It isn't something. Well, it has to do with the word singular. Now, in the English language, when we say singular, what does singular usually mean in English? You know, I have a singular goal in life. You know, singular usually means what? One, like single. The word singular in the English context generally means one, but in a mathematical context, it does not. Singular in mathematics means you're trying to divide by zero in every context. So a simple example, and this is one of my favorite uses of the word, is that imagine you have a star, a huge big ball of flames. That star has a particular mass. Okay, even though its density is very small, because of the sheer volume, it's going to have tremendous mass. Now, we know something about gravity and gravitational pull. We know that any two objects with mass exert a gravitational pull. We know this. And the pull is an inverse square of the distance. So the closer you are, the greater the pull. So if I cut the distance in half, I increase the gravitational pull 4 times, and so on. So this star has a particular mass, has a particular gravitational pull. So imagine the star essentially dies. It collapses upon itself. Now, the mass of the star does not change, but the density does increase, because the density, remember, in this case would be the mass divided by the volume. So as the volume is going down, the density is going up, but also the distance that other objects can approach this thing can get much closer, because they're not at the edge of the star. So what happens is, as I get closer and closer and I get pulled in because I didn't know I was there. Now, when the star eventually collapses, the idea is it literally collapsed to one point. And so what does that do to the density? The density is approaching infinite. What does it do to the gravitational pull? Same thing. And when that star completely collapses, in theory, what does it create, anyone?
A neutron star?
Black hole.
A black hole. What's another name for a black hole? A singularity. The concept is that your volume is approaching zero. So you are approaching infinite density, but you're dividing by zero. That's what the term singularity has to do with. So when we talk about a singularity, now this is in theory, it's not like we can, drive over and check out the black hole, down the street, but it's really cool theory. But that's the concept. A singularity, a black hole, is the concept I'm dividing by zero volume in a sense, but the mass did not change. In a matrix sense, if the inverse does not exist, we say the matrix is singular. Singular bad, okay? Singular is not good. I can't do things with singular matrices that I can do with non-singular. Non-singular means there is an inverse. I know it seems kind of backwards because it sounds like a negative term, but non-singular, good, singular, bad. Okay, so with that said, oops, here's my eraser. What can I do to solve with these things? Well, we're going to go through a really simple problem, and I'm going to show you how we can execute this, because a lot of it is just simple number crunching when you get right down to it. So imagine I have the following system of equations. Maybe something that's easy enough. So I have 2x plus 4y plus z equals 8. I have negative 2x, negative 3y, negative z equals 2. And I have negative 6x, negative 6y, negative 2z equals negative 10. I want to solve this system of equations. Now I know how to do it using a matrix and doing matrix operations. I would like to solve this system using the inverse. So the first thing we're going to do is rewrite this as a matrix product. So put down 2, 4, 1, negative 2, negative 3, negative 1, negative 6, negative 6, negative 2, 8, 2, negative 10. Okay, this is my A. We're calling this the vector of variables, and we're calling this the vector of constants. My goal is to write this vector equals the answer. Okay, I can't do that yet. I don't see it. So what we're going to do is find the inverse of matrix A. So we roll up our sleeves and get ready to do a little bit of algebra. Finding the inverse of a matrix is never complicated, but usually involves some algebra and probably some fractional manipulation and things like that. So what we're going to do is we're going to write matrix A. I'm going to write it a little bit smaller so I can fit everything. And then we're going to augment it with the identity matrix. Now, the idea is I'm going to do row operations on the entire thing until the left-hand half of this looks like the identity. Once the left side looks like the identity, as I mentioned last day, the right side will be the inverse. Now, if the inverse does not exist, then this process is impossible. I won't be able to do that. But if the inverse does exist, we will discover it. So right now I have a pivot of 2. Now, eventually I need a 1 here. I eventually need a 1 here, but I don't necessarily need it in the first step, because then that means I'm going to be doing the whole problem with fractions. So I'll use my pivot of 2, and let's do row 1 plus row 2. And so I have 0, 1, 0, 1, 1, 0. And let's do 3 row 1s plus row 3. And then I'll have 0, 3 of these, that'll be 12 minus 6, 3 minus 2, 3, 0, 1. Now I'm at a very good place right now, because now I have a pivot. Now I have a pivot of 1. Oh, big fan of pivots of 1. Definitely makes my life a little bit easier when I do that. All right, so now let's take this guy, put a 0 above, let's put a 0 below. So we're going to do negative 4 row 2s plus row 1. So 2, 0, 1. Okay, negative 4 of these plus 1, that'll be negative 3. Negative 4 of these plus 0, that'll be negative 4, and then 0. Now we're going to go negative 6 row 2s plus row 3. And we'll have 0, 0. Oh, stays a 1. Negative 6 of these plus this, that'd be negative 3. Negative 6 of these plus this, and then a 1. So once again, I'm in a really good place here. I have my pivot of 1. Okay, so now we'll use that guy to put a 0 here because I've already got a 0 there. So how about negative row 3 plus row 1? So 0, 0, 1, negative 3, negative 6, 1. 0, 1, 0, 1, 1, 0. Okay, and then finally, let's see. I want to go negative this plus this, so that'd be 2, 0, 0. The negative of this plus this, that would be a 0. The negative of negative 6 plus 4 would be a 2. And the negative of 1 plus that would be negative 2. Okay. Now, if I've done this correctly, which I hope I have, okay, let's make sure. Let's see. The last thing I want to do is multiply this row by a half. Okay. So how about 1/2 row 1? Now, hopefully we didn't make any boo-boos. 1, 0, 0, 0, 1, negative 1, 0, 1, 0, 1.
Professor,
1. Yes.
where did that last negative 2?
Oh, did I mess that up? That should be a what? That should not be a negative 2, should it? Negative of this plus this, that should be a negative 1. Thank you. That should be a negative 1. Good catch. We did negative of this plus this, the negative of this plus this, the negative. I don't know why I have a 2 there. Yeah, it should be negative 1. So here, that should be then a negative 1/2, I think, if I did that correctly. Now, we're going to check. Okay. Now, let me do a real fast run through. So when we have this, we're completely ignoring this. This has nothing to do with the process. This only has to do with the final answer. So when I write down my coefficient matrix, 4, 1, negative 2, negative 3, negative 1, negative 6, negative 6, negative 2, 2 for 1, nothing changed. Now I'm using my pivot. So when we add, we add, we add, we add, we add. 3 of these, 1, 3, boom. Okay, that looks good. Then negative 4, go the other way. Negative 3 of these, negative 4. Okay, I'm feeling good. Negative 6, negative 6 of those, negative 6 of those. Okay, and then the last thing, the negative of this, the negative of this, and the negative of this. And now we multiplied through by a half. So if we've made no errors, our inverse is sitting right here. Okay, if we've made no errors. Now, by the way, that's a humongous if. Do you agree? I said, if I've made no errors. Now, let me double check something really quick. I think we're good. So what I'm going to do, I hate doing this, but I'm going to erase. Let's see, because I can't fit that. I'm going to erase right here. Again, hopefully we don't have any boo-boos because I just erased that. It appears that my A inverse, I'll use a different color here. It appears that my A inverse, I say it appears, that means I did it right, is this. So 0, 1, negative a half, 1, 1, 0, and negative 3, negative 6, 1. I am really comfortable with that. I would go out on a limb and say, yeah, that's probably right. Is that good enough? I'm pretty sure that I did it right. Can we improve upon? We're pretty sure we did it right.
We can check.
How do we check?
Don't ask me.
But I love that. You always check. How do you check? You multiply. And what are you multiplying? You're multiplying this matrix times this matrix, and what are you hoping to get as a result? Anybody?
The
The
identity
identity.
matrix.
If I get the identity matrix as a result, then it would be impossible for this to be wrong. If I don't get the identity matrix as a result, then it would be impossible for this to be right. Are you going to make errors along the way? Of course you are. But the check is actually really simple. So we'll do, okay, let's check. So 0 minus 2 plus 3, that's a 1. 0 minus 3 plus 3, that's a 0. 0 minus 1 plus 1, that's a 0. So I have 1, 0, 0 is my first row. 2 minus 2 plus 0, that's a 0. Now I need a 1 in the middle. 4 minus 3 plus 0, that's a 1. That's a good thing. 1 minus 1 plus 0, that's a 0. That's a good thing. Now I'm on to the last row. Negative 6 plus 12 minus 6, that's 0. Negative 12 plus 18 minus 6, that's 0. Negative 3 plus 6 minus 2, that's a 1. It worked. Okay.
And you could have multiplied I'm sorry, you could have also multiplied it the other way, correct? To get the identity matrix?
Yes,
okay.
Exactly. There's no advantage one way or the other. It's just this was to the left of this on my board, so it made sense to multiply that way. But I could have just as easily done it the other way, but I might have got my arms all twisted up, so I like, 1, 2, 3. My first row is 1, 0, 0. You never have to show the check, but it's always assumed you're going to do the check, because otherwise you're saying, I have an answer. Gosh, I hope I'm right. No, I have an answer and I know I'm right. I just checked. This is the inverse. Are we done with the problem at this point? No, but we've done all the heavy lifting. My goal was to solve the system using the inverse. I now can. Because the answer to the system is now X is equal to A inverse times B. Okay, so I'll actually write it out. If I put these side by side, so I'm saying the vector of variables, so 0 plus 2 plus 5, 8 plus 2 plus 0, negative 24, negative 12, that's negative 36, negative 10, negative 46. Okay, well, if I did this right, okay, so how do we check that?
Plug it into one of the original equations.
Yeah. Now here's the nice thing. This is either going to solve all three or it's going to solve none of them, because we didn't find it by using any of the one equations and then, doing all of our back substituting. We did it as a matrix multiplication. So it's kind of an all or none. Let's quick check. 14 plus 40, that's 54, plus negative 46, that would be 8. Good thing. I'll just do the next one for fun. Negative 14, negative 30, that's negative 44, plus 46, that's 2. What do you know? And then finally, negative 42, negative 60, that's negative 102, plus 92, that's negative 10. Once again, celebration. So this is the answer. And by the way, you can leave it in this form. Okay, you can leave it in that form at this point, because it's the form that we set up the problem in. Now, here's the cool thing about the inverse. Realistically, solving a matrix using row operations is absolutely correct. But the inverse can also be used for other things at other times. By the time we get to the end of the course, most of you are going to be so fast and efficient finding inverses that this process is not going to feel so long. Right now, it feels very long, because we have to do all of this number crunching. But you get really efficient and you see things. And the fact is that a lot of times using the inverse is faster than certain types of row operations, strangely enough. Okay, now I'm going to move on from this, because I want to show you some of the properties of inverses now. Again, we found the inverse. We had to do row operations on an augmented matrix. We found something. We believed it was the inverse. No, we automatically check through multiplication. Once I got it, I can now solve this. Solving systems of equations is the first use of a matrix, but it is far from the only use. In fact, down the road, you probably won't even think about solving systems, because we move on from that. That's our intro, but that's not our ultimate goal. And here's the reason. There's multiple ways to solve a system of equations. Think baby algebra, right? If I gave you 2 lines on a plane, you know, you could graph it and read the solution if they're integers. I know I can use substitution. I know I can use the addition method, add them to eliminate variables. I know there are multiple ways of finding the solution to a system that do not involve using a matrix. So if it's possible to solve a system without ever employing a matrix, then a matrix isn't required. It's just usually easier and faster when the problem is bigger. But a matrix actually has so much more value and so much more use than just solving systems of equations. That's really a low-level use of a matrix, but it's the first one we know of, and it's really easy to understand. So what are some properties of the inverse then? Well, this is kind of a neat one. All right. Suppose that A and B are elements of M, N, N. So in English, what did I just say? Anybody? What am I saying about it?
A and B are both n by n matrix.
Exactly. It's just sort of a shorter way of saying that. They're elements of the set of all n by n matrices. I want you to get used to, you know, goofy notation like that, because you're going to see that kind of stuff all the time. This is the same as me saying A and B are n by n matrices. That's just a little shorter. Now, suppose A and B are non-singular. That means A inverse exists and B inverse exists. Okay? What if? Does that exist? A and B are both non-singular. I would like to know about this. Well, it turns out, this is kind of cool. It turns out this is B inverse, A inverse. Assuming A and B, the inverses exist, you notice they're the same size. That means the multiplication will be defined. That's important. The inverse of the product is the product of the inverses, but in reverse order, which is kind of crazy. So I'm going to show you. If I took my original AB and I multiply it by B inverse A inverse. Now we mentioned last day, okay? I'm going to prove this statement here is true. We mentioned last day that matrix multiplication in general is not commutative. You can't just assume you could commute. In fact, there are very, very rare exceptions. Okay. Now, if I'm multiplying something by its own inverse, I can commute those. If I'm multiplying something by the identity matrix or the zero matrix, that's pretty much the exceptions. In general, A times B is not equal to B times A. Matrix multiplication is not commutative, but it is associative. Remember, if you have a product of several things, you can group things any way you want without rearranging them. So the first thing is, I did not rearrange, I regrouped. So A times B, and then that results times this. I can do this, but what's B times B inverse? Well, that's the identity matrix. Now I'll do it this way. And then what's A times the identity matrix? That's A. And then finally, I have A times A inverse, which is, so I've just proved that the inverse of this product is this because we got the identity as a result. Anytime you multiply two matrices together and get the identity, that means your two original matrices have to be inverses. Okay, there's no way around it. So that's kind of a cool property, that the inverse of a product is the product of the inverses in reverse order. Now, what if A and B, what if one of them was singular? Well, then it would turn out the product is not invertible. If one of these guys is singular, then this is not possible because that would mean that I'm claiming both of their inverses exist. No. I started with both of their inverses existing. If one of them doesn't exist, then I can't do any of this process because I would have a singular matrix. Okay, so kind of a neat property of inverses in general. Now, I mentioned a term on the first and second day of class, and I'm going to mention it again today, or actually third day of class. I call it the set of equivalent conditions. And as we go through the textbook, you're going to keep seeing this list added to. So some of the things that we know about equivalent conditions, okay? For example, if I start now with, let me start with a system of equations just to make it easier. Let's suppose A is an n by n matrix. Then we'll say this system has a unique solution if and only if, okay? If and only if A inverse exists, okay? We agree with that. If and only if matrix A is row equivalent to the identity matrix. So that means when we do the Gaussian elimination and I go for Jordan canonical form, that means the coefficient matrix looks like all ones down the diagonal, then the numbers on the right will be my solution. We did that on day one. So if A is row equivalent to the identity, that's the same as saying this has a unique solution. That's the same as saying A inverse exists. When we say equivalent conditions, if one of them is true, they're all true. But also it means if one of them is not true, all of them are not true. And this list is going to have about 10 things in the end. And we like this because it means that if I'm trying to prove something, I may not have to prove every aspect. I may only have to prove one thing, and then all of the other properties are automatically inherited. So if I prove that A inverse exists, then I know that A is row equivalent to the identity matrix. Okay, there's a few other things that are going to go along with it. So now I'm going to introduce a new thing called an elementary matrix. Okay, and an elementary matrix goes along with all of this. So I'm going to show you a really cool process because it's a lot of the way we program technology. Now, understand that we're learning how to do things pencil and paper by hand so we can understand them. But if you had a really, really large problem, you're not going to do it pencil and paper. You're probably going to use technology. But there are limitations, for example. What if I wanted to use a matrix to solve a problem and my first pivot is not a 1? My first number is a 13 or a 7 or just something else. Well, technology requires that the pivot be a 1. So in the first step, right, you're going to multiply through by the reciprocal of something, and fractions cannot be stored. Only real numbers can be stored. You guys, anybody knows technology knows that. Can't store fractions and real numbers simultaneously. So now you have decimal round-off issues. And that's why it's really easy for me to design a problem that a computer will get the wrong answer to, yet you can do it by hand in under a minute because of the size of the coefficients involved. So we have to have backdoor ways sometimes. And this is something I always tell my linear algebra students, because this is when I was in school, we would do this. Try to find problems that technology cannot get right. In other words, if you've ever used a calculator and got a wrong answer, okay, the original TIs, the first graphing calculators were horrific. When you gave it negative input, you often got the wrong answer. When you did a graph, often there was nothing to the left of the y-axis. It didn't do well with negatives. If I took a negative number and raised it to a power, I often got error. If I tried to take an odd root of a negative number, it usually always gave me an error message, even though I know what to do. So trying to find problems that the technology has difficulty with is very important, because if you can, let's call it, mess up the calculator or the computer, then you can start to fix it and improve it. Okay. When I was in school, they were called ill-conditioned problems. To find problems that technology couldn't do, we would find problems that the supercomputer at UCSD couldn't do, but we could do by hand, because they're problems that inherently give us issues because of the numbers. And then once we figure out how to do these problems, we can now improve upon the technology. We know backdoor ways of doing things. You see, so the way a computer solves a problem is not necessarily the way we solve the problem, because we don't have problems of decimal storage and things like that. So here's what I want you to think of. Let me start with a really simple matrix. Let's say my matrix is going to be 2, -6, 3, 4. Okay. And what I want to do is I want to do row operations on A until A looks like the identity matrix. That's a pretty simple concept. And then secondly, I want to show that those row operations actually can be done as matrix multiplications. Kind of a crazy thought. So let's do this. So my first step in the problem, I'm going to take 1/2 of row 1. Okay, so now I have a pivot of 1. Now I'm going to take -3 row 1s and add it to row 2. Okay, and that will give me 1, -3, 0, and 13. Next, I'm going to take 1/13 of row 2. And then finally, I'm going to take 3 row 2s and add it to row 1. Okay, I did it. This took me exactly 4 row operations. I don't think this could be done in fewer than 4. I could certainly have taken longer. So I just basically took this, did some row operations. I got the identity, which means that my original matrix is row equivalent to the identity. So a couple things. One thing, it means that A inverse does exist. Okay. I would like to do a couple of things. I would like to write A and or A inverse as a product of matrices. It's kind of a strange thought, but this, we're going to go somewhere with this. So here's what I want to do. Okay. I would like to figure out if I took the identity matrix and I did this to the identity matrix, what would I get? Take the matrix, in other words, take the matrix 1, 0, 0, 1, and I want you to do this to that matrix. Well, then I would get 1/2, 0, 0, 1. Agreed? That's what I would get. Now, what if I do the same thing? I start with the identity matrix and I take -3 row 1s and add it to row 2 of an identity matrix. Well, let's see, then it would look like this. Okay. What if I did this to an identity matrix? And I'm putting my matrix right under the row operation. If I did this to an identity matrix, I would get this. And what if I did this to an identity matrix? If I took 3 row 2s and added it to row 1, I would get this. Okay? So, okay, that's really neat. I'm going to call this one E1. I'm going to call this one E2, E for elementary, E3, E4. Now, this is kind of an interesting thing what I'm going to do here. I did row operations. I'm claiming that I could do matrix multiplications instead of row operations. What if I took E1 and I multiplied it by A? What would I get? So my E1 was 1/2, 0, 0, 1, and I'm going to multiply that by my original A. Okay. When I do this, what will I get? 1 plus 0, -3 plus 0, 0, 3, 0, 4. Okay. Well, that's exciting. When I took my E1 and multiplied by A, I got this. Oh, that's exactly what I got when I did my row operation. So the row operation that I did, had I done this as a matrix multiplication, I would have gotten exactly the same thing. How interesting. That's always true, by the way. Now, what if I do the same thing, but now I take E2? I'm going to take E2 and multiply it by the result, by that. Okay, what would I get? I'm not going to have enough room here. Let me write it over here. Let me take E2 and multiply it by that result. Well, E2 was this, 1, 0, -3, 1. And I'm going to multiply it by this result because that's where we are in the problem. Now, when I do that row operation, I'm going to get this matrix. What if I do this as a matrix multiplication? 1 plus 0, -3 plus 0, -3 plus 3, 9 plus 4. I think we're onto something here. All 4 of these row operations I performed can be done as a matrix multiplication of the elementary matrices. Interesting. So I'm not going to do this for all four. I'm going to state our conclusion real quickly here. So let's see. I'm going to run out of room. You know what I'm going to do? I'm going to rewrite my elementary matrices. Let's see. I'm going to do it right here. I'm going to rewrite my elementary matrices so I can see them up higher. So there's E3 was 1, 0, 0, 1/13th, and E4 1, 3, 0, 1, because I need the space. Okay, so I have 4 elementary matrices that I'm claiming will do my dirty work for me. If I do a matrix multiplication rather than a row operation. So why would I want to do an elementary? Why would I not want to do a row operation? Because it's far easier to program a computer to do matrix multiplication. And it's way, way, way faster if I want to do this as a computer. So now we realize that based on what I just did, if I do E4 times E3 times E2 times E1 times A, because remember, we started with E1 times A, and then we took our result and did that, and so on. If I do this all the way to the end, I should get the identity matrix. That's what we just did. When we finished these 4 row operations, we ended up with the identity matrix. So if I do this as a matrix multiplication instead, I'm going to get the identity matrix. I would like to undo this. Now, we know the identity matrix exists. So doesn't that mean that this quantity here must be A inverse? E4 times E3 times E2 times E1 would have to be A inverse because that thing times A is the identity matrix. Well, if this stuff here is A inverse, then what does A have to equal? Well, A would have to be the inverse of all of this. And what did we say a moment ago? The inverse of a product is the product of the inverses in reverse order. That means this would have to be E1 inverse times E2 inverse times E3 inverse times E4 inverse. How interesting. I could write A as a product of matrices. Now, I don't want to find 4 inverses. That would take forever. Actually, it won't. This is going to be one of the simplest things you do. Finding the inverse of an elementary matrix does not require work. Remember, what is an elementary matrix? I started with an identity matrix and I did 1 row operation, 1 legal row operation to an identity matrix. That's how I got my elementary matrix. If I want the inverse of that, I just simply undo that operation. So with what I have up here, I'm going to leave that there. I don't need this now. What would E1 inverse have to be? Well, I got E1 by multiplying row 1 by a half. How do I undo that? Multiply row 1 by 2. I'm claiming this is the inverse of this. Let's check. 1 plus 0, 0 plus 0, 0 plus 0, 0, 1. Yep. When I multiply this matrix times this matrix, I do get the identity. So that absolutely is a correct answer. How about E2 inverse? I took -3 row 1s and I added it to row 2. How do I undo that? Take +3 row 1s and add it to row 2. Quick check. 1 plus 0, 0 plus 0. -3 plus 3, that's 0. 0 plus 1, that's the identity matrix. Finding the inverse of an elementary matrix just means you undo the row operation you did. So if you multiplied by a constant, multiply by the reciprocal. If I did a row change, I just change them back. If I added a multiple of a row, then add the opposite sign of that row. So let's continue. E3 So what did I do for E3? I took 1/13 of row 2. So I undo that by taking 13 row 2s. Quick check. 1, 0, 0, 1. And finally, E4 inverse. I took 3 row 2s and I added it to row 1. So now we will take -3 row 2s and add it to row 1. And again, 1, -3 plus 3 is 0, 0, 1. I don't need to physically do that check every time. I'm just doing that to show you. So here's my grand claim that this times this times this times this is going to give me my original matrix A. So let's just do it. I'll write it up high because I no longer need this stuff. I had to find the original elementary matrices in order to find all of the inverses of the original elementary matrices. That was critical. This is the meat and potatoes here. So let's do this. I'm going to multiply these side by side. I'm going to write them out here. And in exactly this order. Order is everything. You can't change the order of multiplication. I hate erasing as I go, but I'm going to do that so I have room because I'm just rewrote those same things. Now, if everything went correctly, when I multiply this out, I should get my original matrix A back. Okay, well, remember matrix multiplication, although not commutative, is associative. So there is a fast way of doing this. Start by multiplying these two. Okay, 2 plus 0, 0 plus 0, 0 plus 3, 0 plus 1, and then multiply these two. 1 plus 0, -3 plus 0, 0, 13. And now finally multiply these two together. When you're multiplying more than 2 matrices, you can only do 2 at a time, but you can certainly group them in such a way that it's convenient. So now 2 plus 0, -6 plus 0, 3 plus 0, and -9 plus 13. And folks, I do believe that is our original matrix A. Whoa. So if I start with a non-singular matrix, we know it's row equivalent to the identity matrix. Okay, that's one of the equivalent conditions. So if I have a non-singular matrix and I do all the row operations necessary to get it to look like an identity, each of those row operations is equivalent to a matrix multiplication of an elementary matrix. That's what we got. So once I figure those out, then I can rewrite A as the product of the inverses, which is crazy. So if the following was true, if I said A, or let's say EK minus 1, dot, 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 E3, E2, E1. This is kind of how we started the problem. Let's assume it takes K of these. Let's assume that's a large number. If A is invertible, then it is row equivalent to the identity. So we're going to do row operations till we get to the identity. Then in this case, A must equal E1 inverse, E2 inverse, all the way to EK inverse. Okay, that's what we just did. So that means I'm adding to my set of equivalence conditions. If a matrix, a square matrix is invertible, then it can also be written as a product of elementary matrices. And this is actually really a powerful one. An elementary matrix is easy to program into a computer. When we're trying to do certain things, what we do by hand, I said, is not necessarily what we do with technology because it might not be as efficient. Some of the things we have technology do would be very inefficient to do by hand. It would take us too long, but the computer can do it really, really, really fast. So I'm really talking about large problems, not small problems. Anything we can do by hand is easy enough, but not, the large problems. So those are elementary matrices. So now we have a good feel, hopefully, how to find an inverse of a square matrix if it exists, how to use that to solve a system of equations. And now I just introduced this concept of elementary matrices. These are very, very powerful tools that we're going to use. Now, I want to show a kind of a cool application of this concept. So I'm going to make reference, hopefully you have a textbook, I'm going to make reference to a problem in an example. Okay, in section 2.5. Now, it doesn't matter what edition you have. I have a ninth, let's see, what do I have? I have an 8th edition. So if I go to, hold on. All right, in the 8th edition, they added an extra section, and it's neither good nor bad, it's just there. I'm looking at section 2.5. Now, there's a really, really cool problem here. It involves something called a stochastic matrix. Now, stochastic is a very, very powerful term, but it's the idea that there is no unused portion of something and there's nothing left over and everything goes to where it's supposed to go. Now, I'm going to read the problem to you. Okay. It's in my 8th edition, it's example 2. In my 7th edition, hold on a second. So if you have an 8th edition, it's page 85, example 2. If you have a 7th edition, which I happen to have right here, it is, oh, it's also page 85. I don't think there was any changes between the 7th and 8th. So it's example 2, page 85 of both editions. That's kind of convenient. So the problem reads like this. 2 competing companies offer satellite television service to a city of 100,000 households. Okay? And basically it goes like this. If you're with cable company A, every year 70% of the people stay with A, 20% leave and go to B, and 10% go to no cable. In other words, they go to the shotgun shack with no electricity and they want to live, like Amish or something. Cable company B retains 80% of their customers every year. 15% go to cable company A, and 5% do the whole shotgun shack, no cable thing. And finally, what if you're a no cable person? Well, if you're a no cable person, 70% of the no cable people stay no cable people. 15% go to company A and 15% go to company B. Now they're saying every year, forever and ever and ever, this is what happens. Now, you notice the percentages have to add up to 100% because every person has to be accounted for. Nobody's dropping off the grid here. Now, it's a little unrealistic, first of all, to say it's going to be the same every year, but it's a good starting point. And if you can imagine, right, this is I call it the cable company problem. And we're going to look at this at the very end of the course as well. But this could be true with anything. This could be true with cell phone companies. This could be true with, cola. That back in the day, there were only 2, right? Pepsi and Coca-Cola, and they're just the same idea. With cell phone companies, it's kind of the same thing. People are switching companies all the time. Some, they retain most of their customers, some switch. The idea is, how can I represent this problem using a matrix? And can I use matrix multiplication to help me along? The answer is absolutely yes. So the way the problem works is there's something called a transition matrix, and I'm going to write it down. Okay. I don't know if you have a book in front of you. So based on what I said, there's cable company A, there's cable company B, there's the shotgun shack no cable people. So 70% are retained, okay? 20% go this way, 10% go this way. This is the given. Cable company B, they keep 80% of their own. 15% go in this direction, 5% go in this direction. Of the no cable people, 70% will stay no cable. It doesn't mean the same people every year, just 70% of them. And then 15% will go this way, 15% will go this way. So you notice every single person is accounted for every single year. Now this leads to what's called the transition matrix. I'm going to call it matrix P. So if I label my matrix this way, I'll put P, sorry, P. this is, make sure, you're going A, B, none, A, B, none. I'm going from here to here. So the columns need to add up to 1, not the rows. So if I'm looking at this in my picture, okay, from B to A, how many went from B to A? From B to A was 0.15. And how many went from none to A? That would be also 0.15. Okay, now from A to B, how many went from A to B? That would be 0.2. How many went from B to B? That would be 0.8. And how many went from none to B? That would also be 0.15. Now the none, how many went from none to A? That was, did I say that right? How many went from, oh, I'm sorry, how many went, sorry, I said it backwards. How many went from A to none? Not none, sorry. How many went from B to none? So B to none was 5%. And how many went from none to none? That's 0.7. Now notice my columns. My columns add up to 1. This is called a stochastic matrix. Stochastic matrix, all of my probabilities, or in this case percentages, they have to add up to 1. Now the rows do not. So you notice this row adds up to 1, this row adds up to less than 1, this row adds up to more than 1. A way to interpret that is over the long run, A is going to kind of stay the same, but more people are going to end up with B and fewer people are going to end up with no cable. That's a simple interpretation. Now, here's the goal in reality, and we're not going to be able to prove this really until the end of the course. Regardless of the original distribution of customers, it doesn't matter what the original distribution is. If you're using a stochastic matrix to shift and shuffle everyone around, eventually you will reach what is called steady state. You will reach a situation where every year it will now stay the same from this point on because of the restructuring. Now, I don't know what the steady state is before I start the problem. So how do I find the steady state? The steady state is found through matrix multiplication. So I'm going to erase this. Now, this is where you would never do this by hand. You would absolutely use technology for this. Matrix multiplication, when you have a stochastic matrix like this, can be really messy really, really quickly. So if I said, let's call X, okay, let's call X the distribution. So I'll put the number in A, the number in B, and the number of nones. Then these three numbers would have to add up to the population. These are not percentages. The original problem said there's 100,000 people. So that would mean maybe I have 40,000 here, I have 50,000 here, I have 10,000 here. It could be whatever you want it to be. I just have to add up to the population. Okay. Now, at any given moment, that's how many people are there. So I have to have a starting amount. So let's call the starting amount of my population, let's call X0. Okay. So what's going to happen is when I have X0, and I multiply X0 by the transition, it's going to tell me what happens, and I will get a new distribution of people. So whatever I'm starting with at the end of the first year, I'm going to have a different distribution, and X1 will equal P times X0. That's the whole point of this. This tells me where everyone went. So in the textbook, the author shows you. Now, you can do this by hand. And as long as I'm using nice big round numbers with thousands in them, it's easy. But after a while, you're going to start seeing decimals, and it's going to get really icky really fast. So this is the kind of problem you really would want to use, a powerful calculator or a computer on. Now, question is, what's X2? Well, X2 would be P times X1. But X1 was P times X0. Oh, so that's P squared times X1. Can you square a matrix? Is that legal to square a matrix? What do you think?
Yes.
If the matrix is square, then p squared is just p times p. Yeah, that's totally legal. Now let's go one more. What's x3? That's p times x2, which is p times, I'm sorry, this was x, sorry, that's x, not x0. And p times p squared times x0, or, oh my goodness, I think I see a pattern here. So dot, 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 xn is clearly p to the nth power times x0. Now, here's what I want you to notice. Every year, I should get closer to what that steady state situation is. Every year, I should get a little bit closer. Similar to Newton's method in Calc 1, when I did repeated iterations to see if I could converge on a decimal approximation. You guys remember where the curve crossed the x-axis, stuff like that. If you don't remember, that's okay. Every year I get a little bit closer. At some point, when I do the next year, it's going to look like the previous year at some point. The problem is this requires a limit as n approaches infinity, because every year is going to be slightly different, more decimals and so on. So it becomes a very impractical problem. Now, if I've got a powerful calculator, I can ask it to do the 5th power or the 10th power or even the 50th power. So in the textbook, the author shows us something. So let me find it again. In the textbook, the author shows us, if I do this process, and he says, well, what if you do it, a couple of years? What if you do it several years? He shows the 10, he does it 15, and then basically says, look, if I keep doing this process, you see the numbers are getting closer and closer to something, and you start recognizing what's going on. And you say, I see decimals like 0.33333. I'm thinking that's probably closing in on a third, stuff like that. The problem is I'd have to do repeated multiplications to see that. And again, without technology, that would be a nightmare to try to do this. Remember, we started using this book in the 80s. We didn't have the technology to actually do this problem when we first saw this problem, but now we have the technology to do this. So what I want you to understand is, through repeated matrix multiplication, I can get an answer, but it's not efficient. We're going to learn another way at the end of the course. We're going to do this problem. Let's see, what day? I'm going to tell you exactly what day. We're going to do this problem on May 9th. I'm going to take this exact problem and do it a different way on May 9th. I'm going to show you how you can find the steady state at the very beginning of the problem. And that, in a nutshell, is the whole point of this course, being able to solve that kind of a problem using all the tools we're going to develop. But that's chapter 7. That's quite a ways away from here. So I wanted to show you this. I don't actually want you guys to sit there and multiply things out. It's not very efficient. But I want you to read the section so you understand the process is, through repeated matrix multiplication on my starting value, I can approach something. So the matrix multiplication gets us to where we need to be. Again, it's not very efficient in general, but as long as I have technology, it can be very, very fast. One of the problems we face is that the distribution is people. And I'm going to start getting decimal values really soon in the process. So it's like, how do you deal with that? That's another issue altogether. Anyway, that's where we are.